Okay, imagine for a second that space itself, the fabric of reality, isn't just empty. What if it could actually hold on to memories? Not like feeling nostalgic, but a literal physical imprint of stuff that's passed through it. Today, we're doing a deep dive into a really mind-bending idea from theoretical physics. It's this concept that space-time might actually keep a memory of matter that's moved through it.
Yeah, it's pretty rare in fundamental physics to get genuinely new ideas, ones that aren't just tiny tweaks. And look, most turn out to be wrong, let's be honest.
Okay.
But this one, well, it's intriguing enough to really take a proper look at. It's different.
Yeah. Right, that sets the stage perfectly.
Yeah.
So our mission here is to unpack this fascinating theory. We'll look at what it's actually claiming, some really surprising things it suggests about, the biggest mysteries out there, and yeah, the big criticisms too. We want you to get a handle on what this could all mean for how we understand the universe. Okay, let's kick things off with gravity. We sort of take it for granted, right? But it's actually pretty unique among the fundamental forces. One key thing is that gravity's field apparently holds, well, what physicists call redundant information about particles. Like it knows more than it needs to.
That's exactly it. When we say redundant information, specifically for gravity, we mean details like a particle's mass, its momentum. And what's really interesting is it can indirectly sense electric charge, too. Not directly, but it feels the energy in the electric field. And that's a huge difference because, say, an electric field, it tells you nothing about the mass creating it. Gravity's just more comprehensive somehow. It senses more stuff.
Okay, this next bit is where it starts getting really interesting, I think. This new idea actually kind of builds on something already predicted by Einstein's general relativity, though it sounds pretty weird. It's called gravitational memory. The basic idea is that when really huge things, like black holes or neutron stars, smash together, they don't just send out a quick ripple of gravitational waves, they actually distort space-time in a way that lasts.
Right. And the really counterintuitive part, the surprising prediction, is that after the waves pass and things quiet down, tiny test masses, just imagine little free-floating things, would actually be permanently moved from where they started. It's like space-time gets stretched or squeezed and then just stays that way, a permanent deformation. And this gravitational memory, well, scientists are actively looking for it in the data from places like LIGO, the gravitational wave detectors. But no confirmation yet. It'd be super subtle.
Okay, so that's the sort of known but unproven gravitational memory. Let's switch to the core of this new idea, which is much more speculative. So you need to picture space-time not as smooth and empty, but like
Hmm.
a grid made of microscopic quantum bits. These are like the absolute smallest possible units of information, way, way smaller than atoms, down at the Planck scale, which is like the fundamental limit of tininess in the universe.
Mm-hmm. And the proposed mechanism is actually pretty neat. When a particle, any particle, moves through this grid, it interacts with these tiny quantum bits. It leaves a trace, a memory. And here's the key bit. Because of quantum rules, specifically something called the no cloning theorem, which basically says you can't perfectly copy unknown quantum information matter, over time actually loses some of its information to space. It's not destroyed, you see. It's just transferred,
Yeah.
imprinted onto this space-time grid.
Wow. Okay. So if that's happening,
Yeah.
what does that actually mean? What are the consequences for the really big questions in physics? You mentioned things like the black hole information paradox or dark matter. It sounds huge.
It really does. And that's why it's grabbed attention, despite being so speculative. The theory suggests two massive implications. First, it might, just might, solve the black hole information paradox. The problem of what happens to information that falls into a black hole. Is it destroyed? That violates quantum mechanics. This theory says, well, maybe it's not destroyed at all. Maybe it just gets transferred out of the black hole and imprinted onto the surrounding space. The information escapes, becoming part of this universal memory.
So it's not gone, just stored differently.
Exactly.
Yeah.
And the second implication is maybe even more startling. It could potentially explain dark matter. The idea is if this stored information, this memory imprinted on space, carries energy, and energy has mass via EMCMCOS, then this stored energy could literally be dark matter, the collective weight of all this imprinted information throughout the universe. And the proponents even claim that if you estimate how much energy could be stored this way, it roughly matches the amount of dark matter we think is out there.
Whoa. Okay, hold on. Solving the black hole information paradox and explaining dark matter with one idea, That's not just a big claim. That's like rewriting fundamental physics. It changes how we think about what black holes even are, or what most of the universe is made of. But okay,
Hmm.
something that big, it's got to face some serious pushback, right?
Yeah.
What are the main criticisms? Where does it fall down?
Right. And what's interesting is the source material we looked at, written by a physicist,
Mm.
is very upfront about the problems.
Hmm.
He doesn't hold back. There are two really big ones that make him classify it as, well, highly speculative. First, there's a major energy conservation problem. If dark matter's energy comes from this memory process, this information transfer, where did that energy originally come from?
Mm.
Standard cosmology, our current best picture, says dark matter formed way back in the early universe, alongside normal matter. This theory suggests dark matter is kind of created later as matter moves around and loses information. That creates a real headache for the universe's overall energy budget. It's like energy appearing from nowhere, which physics doesn't like. It's a big counting issue.
Okay, that sounds like a pretty fundamental problem. What's the second major criticism?
The second one gets a bit technical, but it's about the Planck length itself, that fundamental tiny scale where these memory bits supposedly live. The issue is, in Einstein's relativity, any length, even the Planck length, isn't necessarily fixed. It can stretch or shrink depending on how fast you're moving or the gravity around you.
Right, length contraction and time dilation.
Exactly. So if the pixels of your memory grid can change size depending on the observer, how can they reliably store information in a consistent way? Defining a fixed size for these bits is problematic within our current understanding of physics.
Hmm. Yeah, that seems tricky. So given these pretty big issues, what was the author's final verdict?
Well, he put it pretty bluntly. His assessment, considering these unresolved problems, was a 10 out of 10 on the crackpot meter.
Ouch. 10 out of 10 on the crackpot meter. That's quite a
Yes.
rating. But, even with the score like that, maybe there's still some value in thinking about these really out there ideas.
Oh, absolutely. I think that's a crucial point. If we zoom out a bit, even if this specific theory has major holes right now, that core idea space never forgets is provocative. It could still spark new lines of thought, maybe inspire different, more rigorous mathematical approaches. Sometimes asking these huge, maybe flawed questions is what pushes science forward,
Hmm.
forcing us to re-examine things we thought we knew, even if the initial idea doesn't quite pan out. It's part of the process.
Yeah, that makes sense. And it's been quite the journey exploring this one. From this really intriguing possibility that space remembers, to these huge claims about solving massive cosmic mysteries like black holes and dark matter, and then hitting the hard wall of these major scientific challenges. It really shows how much we're still figuring out.
It really does. It's a great example of how science works, right?
Yeah.
It's not always about finding the perfect answer immediately. Sometimes it's about asking bold questions, pushing boundaries, and seeing where the investigation leads, even if it leads to more questions.
Well, it definitely gives you something to think about. And like the author joked, maybe if you ever feel like the universe is holding a grudge against you, perhaps it literally is, keeping a record somewhere in the fabric of space-time.